All right, today we're going to go through rate of change, the squeeze theorem, and limits of compositions and discontinuous functions. The nice thing about rate of change is you guys have talked a lot about this before in Math 2 and Math 3. So we're just going to do a nice review of it. This is going to come up really big throughout calculus. So it says another meaning for slope is rate of change. In this course, there'll be two situations where you use slopes. Okay? The first one is average rate of change. So this is the slope between 2 points on a graph, or the rate of change between 2 points in time. It's found algebraically using the method from previous courses, right? This is just a slope formula. That's it. Average rate of change is the same as finding the slope between 2 points. It's abbreviated a lot of times. You'll see this AROC abbreviation in the book, right? It just stands for average rate of change. Okay, what's going to be new to us is instantaneous rate of change. So this is the slope at a single point on a curve, or a single instant in time. We can approximate that using average rate of change. Later on in chapter 2, actually, or unit 2, we'll go through and show you how you can use calculus to find that. But for now, we're going to focus on just approximating it with using average rates of change. Just a quick example of that. If you think of a graph, we got a curve. So average rate of change is, I want to find I pick a point, an x value there, and I pick an x value there. If I want to find the average rate of change, I'm just finding the slope of that line that passes through those 2 points. And then what it's talking about there is we can use that to approximate, if I want to find the slope of that at that point right there, that line, I can't tell the exact instantaneous slope, but I can approximate it using that average rate of change. Now again, later in calculus, we'll actually be able to find that instantaneous rate of change, that change in that moment. So this says, right, given that function, find the average rate of change of f of x between 2 and 3. So again, all we're doing is I need to know the coordinates of both of those points, and we're just going to find the slope between those 2 points. Well, I know x equals 2 and x equals 3, but I don't have the y values. So let's plug both of those in there and find the y value. So if I plug 2 in there, I see 2 cubed is 8. 2 squared is 4 times 2 is 8. So you got 8 minus 10. Plug 3 in. So you got 27 minus 18. That'd be 9 minus 1. That's going to come out to be -1. Okay, all we're going to do now, right, find the rate of change. So I just go y minus y over x minus x. So I'm going to take my y coordinates. I'm going to go -1 minus -10. And you make sure you go the same direction. So I go 3 minus 2 with the x coordinates. That changes to a plus. Whoops, sorry. Changes to a plus. That was bad, but it's -1 plus 10. That comes out to be 9. And then 3 minus 2 is 1. So in that case, the average rate of change, or AROC, right? AROC is equal to 9. Okay, find the average rate of change of f of x between 3 and 4. Well, when x equals 3, we already have the y coordinate, right? It's 3, -1. Let's find out what y is equal to when x equals 4. So plug 4 back in there. 4 cubed is 64. Let's see, 4 squared is 16, times 2 is 32. So 64 minus 32 is 32. Minus 10, so I think we end up with 22 there. Okay, let's find the average rate of change. So y minus y, 22 minus -1 over x minus x. Well, again, that changes to a plus. We end up with 23 over 1, or 23. That's the average rate of change. So C says, which of these is most likely to be a better estimate of the instantaneous rate of change at x equals 2.4? Just think about that for a second. Think about what your answer would be. Are we good that it would be this one right here? Right, 2.4 is between 2 and 3. So if I find the average rate of change between 2 and 3, that's going to be a lot closer to the instantaneous rate of change at 2.4 than if I go between 3 and 4. Hopefully that makes sense. All right, so now talking about talking a little bit about time and applying it, our rate of change to this. It says the data in the table shows the mileage from the start of a 4-hour car trip recorded at 1-hour intervals. Assume the car continued in the same straight line. Okay, so it says time in hours, right, and miles from start. It says find the average rate of change, or the average speed of the car for the final 2 hours of the trip. So let's do that. Final 2 hours of the trip. So that would be from time equals 2 to time equals 4. Right, that's the last 2 hours. So I just do a y minus y. In this case, the y is my miles. Right, we're doing miles per hour. So miles goes on top. So 250 minus 120 divided by 4 minus 2. So that's going to come out to be, let's see, 250 minus 120 is 130. Divided by 4 minus 2 is 2. Divide those, you get 65. So those, over the last 2 hours of the trip, that was the average speed, or the average rate of change. B says estimate the instantaneous speed at 1.5 hours. Okay, so I want to estimate it. So if I want to figure out how fast I was going, right here, right, at 1.5 is right between 1 and 2. I'm going to use these 2 points right here. I'm going to go from what was my average from the first hour to the second hour, and that should give me a good approximation. So I'm going to go 120 minus 55 over 2 minus 1. So that would be, what, 65 over 1. So we'd say, if I were just going to estimate or approximate, I'd say we're going about 65 miles per hour. Again, we don't know exactly what's happening. You could be going a lot faster or a lot slower, but that's the average from 1 hour to 2 hours. That's our best estimate. C says, during which hour does the data suggest the car reached the greatest instantaneous speed? So just, it's going up by 1 each time here, right? 1, 1, 1, and 1. So we're just going to say, you know, finding the instant, we can really just compare how many miles you want. This was 55. This was, what do we say, 55 to there was 65, 60, 70. So that was 70 miles in 1 hour, so that would be, we'd say, between 3 and 4. Okay. Pretty easy stuff. All right, we're going to move past that, so that's average rate of change. We're going to talk about the squeeze theorem. What the squeeze theorem says is if you have a function whose y values are always between 2 other functions, and if you look at the outside function, right, the function below and the function above, if as they approach C, if they have the same limit, and my function g of x is always between them, it will have the same limit also. So read that informally. It says if a function g is squeezed or it's sandwiched between 2 other functions, then the same limit, then g also approaches the same limit as the other ones. Here's a visual of that. Let's look at this next example because it has a good visual. So it says the graphs of x cubed over 2x and negative x cubed over 2x are shown, like they're over here on the right side. It says find the limit as x approaches 0 of f of x. So, by the way, real quick, it doesn't tell us which one is which, right? This one, though, right, look at f of x. If I plug in positive numbers, I'm going to get a positive back out. That means as x gets bigger, this has to be positive. So the one right there outlined in red has to be f of x. G of x, if I plug in positive numbers, I get a negative over a positive. So it's actually getting smaller. So it's going to be, this is, I'll outline it in another color. That one's g of x right there. So g of x is in blue, f of x is in red right there. So it says find the limit of f of x as x approaches 0. Well, right, if I come from the left side, the y-coordinate is getting closer to 0. I come from the right side, the y-coordinate is getting closer to 0. Remember, it doesn't matter what happens at that point. It matters what happens as you approach that point. So we'd say this one, the limit is equal to 0. Okay, g of x, we're going to get the exact same answer, right? As I approach on g of x, as I get closer, x gets closer to 0, the y-coordinate gets closer to 0. I guess I should, if I write this with limit notation, right? The right notation, it should look like this. So they both have the same limit. So 4 says the graph of a third function, k of x, is shown. So we look down here below. We'll use our pretty colors. There's f of x. There's g of x, right? And then we got this function in between that's traveling along here. This is k of x. So it travels, and it's always between the 2 functions. That's what the squeeze theorem is talking about. You have 2 functions, and you have a third function that's sandwiched between them. And it tells us right here that k of x is always between g of x and f of x. So it wants me to find the limit of k of x as x approaches 0. What the squeeze theorem says is if the top function has a limit of 0, it's getting closer to 0, and the bottom one has a limit of 0, is getting close to 0. That means my sandwich function, k of x, it's in between, it has to have the exact same limit. So we'd say the limit of k of x as x approaches 0 is also equal to 0. To me, hopefully this kind of just, we just use common sense here, right? If the function's always between the upper one and the lower, you'll get, it will be equal to whatever their limit is. It has the same limit at that point. So that's the squeeze theorem. Okay, next up is, we're going to talk about what happens when you try to find the limit of the composition of functions, like how we're going to approach this. Well, actually, this first one's not, well, we're taking a function and doing something to it, right? So I have f of x over on the right side. It wants me to find the limit as x approaches 3 of f of x squared over g of x plus 1. This is kind of the cool thing, is I can actually just find the limit of f of x right there and plug that in, square it, and then down here I can just find the limit of g of x and add 1 to it. So let's find the limit of f of x as x approaches 3. So if I come over here, on f of x, as I get closer to 3 from the right side, from the left side and the right side, they're both getting closer. It's continuous, right? It gets closer to that point, which is just 3. So we know the limit as x approaches 3 of f of x is 3. Now, because of that square, I'm just going to square my answer, square 3. Okay, next I'm going to find the limit as x approaches 3 of g of x. So I come over to g of x. As I get closer to 3 right there, this graph is getting closer to 2 as I come from the left side and 2 as I come from the right side. So that is the limit as x approaches 3 of g of x is equal to 2. So we put the 2 down there, plus 1. And we just worked that out. 3 squared is 9, 2 plus 1 is 3. So the answer would be 3. So kind of the cool thing is if you take a function and you do something to it, you square it, you add something to it, or subtract something from it, all I do is I find the limit of that function as it approaches the number we're given. Okay? And then once I have my answer, I just plug it into this and square it, or I add 1 to it like I did down below. 6 is tricky because now we have the composition of functions. So what I'm going to start with is just kind of like we did up above, I'm going to ignore the outside part g. I'm just going to focus on f. So as x gets closer to 2.5 down there, what does f of x get closer to? So let's go to 2.5. Well, 2.5 is somewhere in here, right? So somewhere right up there. So as I get closer to 2.5 from either side, my y-coordinate is getting closer to 3. Okay, this is a trick. This is what we do next, is I say the limit of as x approaches, I replace the 2.5 with what I got when I found the limit of f of x as it approaches 2.5. So my answer was 3. So all I did is I found the limit as x approaches 2.5 of the inside part. I found my answer, and now I'm finding the limit of the outside part as x approaches that new answer. So as x approaches 3 on g of x, we just did that one, right? As x approaches 3 over here, it's getting closer to 2 on either side. So my answer is 2. So start with the inside part, find the limit as x approaches the number. Once you have your answer, you're going to set up a new limit with the outside one. And when you do that, instead of going to 2.5, you're going to the answer I got from the first part. All right, 7 is really kind of trippy, weird, it plays with your head a little bit. So follow me here. It's just a little bit different. The first part's similar, right? I'm saying, what is the limit as x approaches 3 of g of x? So let's start with that. So I come over to g of x. Now I want you to notice something. As I get closer to 2, my y values are all below 2, right? I got like 1.5, 1.6, 1.7, 1.8, 1.9. As I come from this side, it does the same thing from the right side, right? 1.5, 6, 1.7, 1.9. So when it's approaching 2, it's approaching only from numbers smaller than 2. So now I'm going to set up my new limit. I'm going to say the limit f of x goes here of my outside function as x approaches. Now this is a tricky part, is when I get closer to 3 on g, I'm only coming from numbers that are less than 2. So I'm going to say as I approach x from the negative side of f of x, and that's going to be my answer. And again, that was because all my values as I got closer, I was only coming from numbers smaller than 2 or to the left of 2. Okay, now I just have to come over to this graph and figure that out. So as I approach 2, 2's right here, but I'm coming from the left side, right? Numbers smaller than, I'm going to get numbers smaller than 2. My y value is getting closer to -1. And that's our answers right there. So those compositions can get a little bit tricky. Just try to think them through. Always start with the inside, so find the limit as x approaches the given inside. You're just looking at the inside of the function. Limit as x approaches the answer to the first limit problem. They're a little bit tricky, but once you get used to them, they're actually not bad. This assignment really is going to be a lot lighter than a lot of them. I mean, there's some new concepts here, but as far as the actual work or the actual problems, I think it'll take you a lot less time, and I think they're a little bit simpler too. Most of us tend to do really well with these. All right, guys, appreciate you listening.